So far, we've been talking about frames of reference moving at a constant velocity relative to one another. Now I'm going to do the experiment with the dropping ball again, only this time the cart will be accelerated relative to the Earth frame. These weights will fall and give the cart a constant acceleration. I'll put the ball up, and then I will release it. The motion is very fast, and I want you to watch at the point where the ball is released from the fixed camera. Ready? I don't know whether you saw that or not, but the path of the ball was the same as it was before, only this time it landed in a different spot. This is because the car kept on accelerating in this direction as the ball was falling. Now I'm going to let you see it again with the slow motion camera fixed onto the cart. This time you saw the ball moving off to one side and not following down the vertical reference line as it did in the constant velocity case. Now suppose you were in this accelerated frame of reference. How could you explain this motion? Gravity is the only force acting on this ball, so it should fall straight down. But if the law of inertia is to hold, there must be a force pushing sideways on the ball in this direction to cause it to deviate from the vertical path. But what kind of a force is it? It isn't a gravitational or an electric or a nuclear force. In fact, it isn't a force at all as we know one. So we're left to conclude that since there is no force that could be pushing in this direction on the ball, that the law of inertia just does not hold. This is a strange frame of reference. We call a frame of reference in which the law of inertia holds an inertial frame. The law of inertia holds in the Earth frame of reference, so it is an inertial frame. The cart moving at constant velocity relative to the Earth is an inertial frame, but the cart which is accelerated is not an inertial frame. Because the frame of reference that we're used to living in is one in which the law of inertia holds, when we go into a non-inertial frame, like the frame of the accelerated cart, our belief in the law of inertia is so strong that when we see an acceleration of the ball sideways, we think there is a force causing it. So we make up a fiction that there is a force. And sometimes we call this a fictitious force. Fictitious forces arise in accelerated frames of reference. The frame is accelerated in this direction, so you in the frame see an acceleration of the ball in this direction, and you say that there is a force causing it.
What's happening this time? Why doesn't the puck move straight across the table as it did before? As you can see, it doesn't. So, if we believe in the law of inertia, then we must believe that there is an unbalanced force to change the velocity of the puck. But this puck is nearly frictionless, so what can be exerting this unbalanced force on it? Suppose that you watch the motion, this time, through a camera which is fixed in the Earth's frame of reference. I think if you concentrate on watching just the puck, you can see that it is moving in a straight line. and that therefore there is no unbalanced force acting on it. Now we're going to stop this rotation so that I can talk to you about what is happening here. I don't know about you, but I'm dizzy. In the Earth fixed frame of reference, there was no unbalanced force, but in the frame of reference rotating in this turntable, there was an unbalanced force because the velocity of this puck kept changing. This was a fictitious force. The rotating frame is a non-inertial or accelerated frame, just as the accelerated frame of the cart that Dr. Hume showed you was. You know that every object which is moving in a circle has an acceleration towards the center of the circle. This is the acceleration that has a special name, the centripetal acceleration. Now you hold this puck for a while, hold it steady, while the turntable is rotating, and I'll get off. Are you ready? I'm ready. Start the rotation. You can see that now the puck is moving in a circle. Dr. Hume is exerting a force to keep it moving in the circle, and you can see this from the fact that the rubber ring is extended. He is exerting the centripetal force, and this is the only horizontal force acting on the puck. But now let's look at it again from his point of view in the rotating system. He is exerting a force towards the center of the table, and yet the puck is standing still, or at least more or less still. There is some vibration. Now he believes in the law of inertia, so he thinks there's an equal force on the puck away from the center of the table, so that there is no unbalanced force. This outward force on the puck is the fictitious force in this case. Sometimes it's called the centrifugal force. In the fixed reference frame, there is no outward force on the puck. Now suppose that Dr. Hume stops exerting a force. Watch the puck. In the fixed frame of reference, the puck moves off in a straight line. There is now no unbalanced force acting on it. Now let's look at it again from his point of view in the rotating system. When he releases the puck, which to him was at rest, it moved. The force away from the center is now an unbalanced force on the puck to him. Remember, to us, the outward force on the puck is fictitious because in our Earth frame of reference it doesn't exist. But to Dr. Hume, in the accelerated frame of reference, it's a perfectly real force.
I hope by now Dr. Ivy and I have convinced you that a rotating frame of reference is not an inertial frame. Now, you've all been told that the Earth is rotating about its axis, and that also it travels in a nearly circular orbit around the Sun. Why then do we find that in a frame of reference attached securely to the Earth that the law of inertia seems to hold? Why don't we observe fictitious forces? The size of the fictitious forces which we have to introduce in a non-inertial frame depends on the acceleration of the frame. The smaller the acceleration is, the smaller the fictitious forces that we introduce. Now, here is a frame of reference attached to the equator of the Earth. The acceleration of this frame is really very small. Because the Earth is spinning about its axis, it has an acceleration directly inward of 3/100ths of a meter per second squared. So on a 1 kilogram mass at the equator, there is a fictitious force acting directly upwards of 3/100ths of a newton. But this is masked by gravity, which is a force downward of 9.8 newtons. So the net downward force is smaller than that of gravity alone. So if I dropped a mass of 1 kilogram at the equator, the acceleration would be slightly smaller than that due to gravity alone, but not really very much. Now, the acceleration of the Earth in its orbit is even smaller still and produces even smaller effects in our frame of reference. Now, I said that the Earth was rotating about its axis. How do we know that this is so? Well, if you take a time exposure photograph of the stars, they seem to be moving in circles about the pole star. But all motion is relative. Is there any way of telling which is moving, the Earth or the stars? The fact that it is the Earth which is rotating can be demonstrated by means of a pendulum. If I set a pendulum swinging, it swings back and forth in a plane. Now, it turns out if this pendulum were at the North Pole of the Earth, the plane of swing would remain fixed relative to the stars, but would rotate relative to the Earth. Now, I'll have to show you what I mean. This pendulum is at the center of this turntable, which will represent the Earth. Now, I'm going to start the table turning around in this direction. I'll put a black arrow on so that you'll remember. All right, start the rotation. The pendulum is at the North Pole of the Earth, and you are in motion as you ordinarily do, standing on the Earth. The plane of swing rotates in the opposite direction from the rotation of the turntable and at exactly the same rate. Now look at it from the fixed camera, which will represent the frame of the stars. The turntable, the Earth, rotates, but the plane of the pendulum remains fixed. A pendulum used for this purpose is called a Foucault pendulum. You saw me start one at the beginning of this film. Let's look back again now. This Foucault pendulum drops sand as it swings. I think you can see the faint line where the sand trail began. The amplitude of swing is decreasing. The sand trail isn't as long now. But the important thing to see is that the plane of swing has been rotating during the half hour that we've been talking to you.
An inertial frame of reference is one in which the law of inertia is valid. All frames of reference moving at a constant velocity with respect to an inertial frame are also inertial frames. We use the Earth as an inertial frame of reference, but it is only approximately one. It has a small acceleration with respect to the stars, for example. The frame of reference of the stars is the best we can do when we look for a frame of reference which is, for all practical purposes, fixed.
An accelerated frame of reference is not an inertial frame. And when we are in an accelerated frame, we have to introduce forces, which we call fictitious forces, in order that the law of inertia and the other laws of physics don't change.